This video presents the experiments for our paper, Model Predictive Control for Dynamic Quadrotor Bearing Formations, accepted for presentation at ICRA 2021. In this paper, we show how decentralized model predictive control may be used to control formations of quadrotors with inter-robot bearing measurements, here extracted from motion capture, but potentially extracted from onboard cameras. The formation is manually piloted in yaw and along the y-axis of the arena, while an autopilot keeps the formation centered along the x-axis at a given height and scale. In this first experiment, we use a three-drone formation defined by a complete graph. The formation is piloted at speeds exceeding 4.5 meters per second and accelerations exceeding 12 meters per second squared. Beginning from an initial hovering position, the three quadrotors are given three successive desired shapes, corresponding to the three major peaks of bearing error magnitude seen on the blue graph at the bottom. The desired formation shape can be seen on the bottom left side of the video, and the quadrotors are highlighted with the corresponding color from the diagram to facilitate the comparison with the desired formation. In between the switches in desired formation shape, a desired velocity along the major axis of the arena is given by joystick. This is the dark green line in the graph below. The component of each quadrotor's velocity along the same axis is shown as a light green line on the same plot. To follow along better, there is a scrolling window to the right with a reduced time span of 5 seconds. It can be seen that even for large step velocity inputs, the quadrotors track the steering command quite well, although with a time lag of several tenths of a second. There are small spikes in bearing error when large velocity steps are given, otherwise good formation convergence properties are observed. A similar experiment is repeated with a formation of four quadrotors and a heterogeneous bearing graph. Because of the increased formation volume and more aerodynamic interference between quadrotors, this formation is piloted slower with speeds of 2.5 meters per second and accelerations of 8 meters per second squared. With the reduced aggressiveness of the pilot, it can be seen that there is little influence between the steering and the formation control. A significant component of the steady-state bearing error is likely due to the downdraft disturbances between the quadrotors and also to a poor identification of the thrust coefficients of the quadrotors. When a sinusoidal-like velocity trajectory is seen in the velocity graph at the bottom, it is due to the major axis component of the velocity induced by a rotation of the formation about its center of mass. Future work on this subject will deal with a more realistic implementation using bearings extracted from monocular cameras for a truly decentralized controller. We will also investigate issues encountered during experiments such as controller singularities, local minima, and collision avoidance. We thank the region Pays de la Loire of France, the École Centrale de Nantes, and the Natural Science and Engineering Research Council of Canada for their financial support of this project. More technical details may be found in the paper.